Hello everyone, my name is Costa from School of Engineering at Deakin University. I'm glad to present our work here today on experimental study of cyclic swell-shrink behavior on an expansive soil. I would like to acknowledge my co-authors, Dr. Wijesooriya and Professor Kodikara from Monash University. In this presentation, I would like to give you a brief background on expansive soils first. Expansive soils, or some people call it reactive soils, covers about 1/5 of Australia's surface soil cover. They are present in many other countries as well in similar volumes. They undergo substantial swelling and shrinkage in response to change in moisture content. Large volume changes are a problem in any geotechnical application. Unnecessary swelling and shrinkage can damage structures built up on them. The amount of volume change in soil depends on the mineralogical composition of it. But the volume change behavior can be assumed to be similar to any expansive soil, since it will only vary in degrees. As a result, many people have studied the swelling and shrinking behavior of expansive soils. However, most of these studies are limited to a single wetting or drying cycle. But in real life, soils are subjected to seasonal changes and undergo multiple wet-dry cycles. So therefore, in this study, we designed to study the swell-shrink behavior of an expansive soil under multiple wet-dry cycles. I would like to give you the theoretical background for our study before I describe the experiments. Now, when the stresses are analyzed in terms of moisture content variation, the potential strain can be obtained using a constant of proportionality known as the hydric constant, alpha, in this equation here, and the difference of moisture content. This is similar to the heat flow analysis, as most of you are familiar with. Here, the delta epsilon SH is the shrinkage strain change, and delta W is the moisture content change. So hydric constant alpha is the proportionality constant. Based on the MPK framework, which was put forward by Professor Kodikara some time back, we can show that alpha has a relationship like this. So in this relationship, alpha is related to specific gravity and void ratio, initial void ratio, with another coefficient. We call this hydric coefficient, a variable, alpha star. So in this study, we investigate the behavior of alpha star. We describe the volume change of expansive soils. Experiments were done using an expansive soil found in Altona North in Melbourne. There are several tests available to observe swell-shrink behavior. Here we used one-dimensional odometer test. However, this is not the conventional odometer apparatus. We modified this apparatus at Monash University to tailor the needs of these experiments. A cylindrical specimen of diameter 76 millimeter and height 12 millimeter were prepared. Initial moisture content was set to 1% dry of optimum moisture content, and the tests were continued for several wet-dry cycles. In total, about 50 specimens were tested. For full details of the experimental procedure, please refer to the paper. I would like to pressing the results starting from the vertical displacement. Here you can see the maximum and minimum vertical displacements observed during wetting and drying cycles. To look at the first cycle, initial wetting and initial drying have different vertical displacements variations. The next cycle shows a repetitive variation. At the end of the cycles, you can see that Aldona clay shows more than 30% net expansion from the initial height. Here, we have plotted the relationship between the moisture ratio and the void ratio for the first cycle. So this is the average. These are the average values for all the test specimens. The initial point you see here, the starting point, indicates the point where a sample was compacted. In this first cycle, so this is the first cycle. This first cycle, curves are unsettled and behave a little widely. However, as we move to the fourth cycle, as you see on this figure, they settle down and converge to a stabilized curve. So this is what we call environmentally stabilized state. Okay, so what happens to the hydric coefficient during these cycles? Here is the relationship of hydric coefficient alpha star with the number of cycles. You can see that alpha star shows similar behavior in all swell-shrink cycles, although there is a little variation in the first cycle in comparison to the other cycles. One interesting point is similar variation of alpha star values can be observed for both shrinking and swelling curves. Let's look at this in a slightly different way. Here we have plotted the variation of alpha star with moisture ratio. The behavior I mentioned therefore, the behavior I mentioned before can be seen more clearly now. You can also see that at low moisture contents, alpha star is low and it increases with the moisture content approximately up to 1, reaching a peak. And then it stays there for some time, for a substantial period. And then it starts to come down towards the end of the cycle. So what can we conclude from these experiments? So we can conclude that hydric coefficient alpha star shows similar behavior during wetting as well as in drying. Values of alpha star increases with moisture content, reaching a peak around 1 before it starts to come down. Now, many people have used alpha, the hydric constant, in desiccation cracking analysis. Now, people use hydric constant alpha as actually a constant, but behavior of alpha star asserts that alpha is not actually a constant. It has a variable nature. But we can suggest that it is reasonable to assume a constant value for alpha over small intervals of moisture content change. For large moisture content changes, we can use alpha incrementally, a constant value for alpha incrementally. Thank you.